Example 5.13 or 6.13 for the given textbooks. For details, please see the description below. An insulated 8-meter cube rigid tank contains air at 600 kilopascals and 400 Kelvin. A valve connected to the tank is now open and air is allowed to escape until the pressure inside drops to 200 kilopascals. The air temperature during the process is maintained constant by an electrical resistance heater placed in the tank. The goal of the problem is to determine the electrical energy supplied to air during this process. We're going to start by writing the mass balance. We simply have the mass going in minus the mass leaving is equal to the change of the mass in the system. Notice that this is an unsteady problem, so the change in the mass in the system is basically the final mass minus the initial mass. Notice that in this case there is no mass entering the system because the air is allowed to leave, so mass entering is equal to 0. And what we have, so this cancels out, basically what we have is the mass exiting is equal to the change of mass at the end minus what we have initially. And then if we write this, the mass leaving is equal to the initial mass minus the final mass. We could do the same analysis for the energy in minus the energy leaving is equal to the change of the energy in the system. That means that is the final energy minus the initial energy. Notice that in this case we are going to neglect the changes in potential and in kinetic energy, and we're going to for the entering of the system we are going to use enthalpies, and for the final states we're going to use internal energies. So we simply write the amount of energy going in is going to be the mass in times the enthalpy going in, and the amount of work produced by the resistance, that's going to be the work. The electrical that is also going in, and the amount of energy leaving is going to be mass out and the enthalpy out, and that is equal to the final mass and the final internal energy minus the initial mass times the initial internal energy. Once again, the amount of mass going in is equal to 0, so this value is going to be equal to 0. Now this is what we need to solve for, the electrical energy. So the electrical energy going in is going to be equal to mass 2 U2 minus M1 U1 plus the exit mass and the exit enthalpy. These are the equations that we're going to use to solve for the electrical energy supplied to the system. In order to do that, we need to first find what is the initial and the final mass that we have in the system, and that we're going to do it by using ideal gas law. So the mass at the initial state is simply the pressure at the initial state, the volume at the initial state, divided by the constant of air and the temperature at the initial state. So the initial pressure is 600 kilopascal. The initial volume is 8 meter cubed. The constant for air is 0.287 kilopascal meter cubed kilogram Kelvin, and the initial temperature is 400 Kelvin. We solving these values, we find that the initial mass is equal to 41.81 kilograms. We do the same process for M2. This is B2, B2, R, T2, and we substitute. The final pressure is 200 kilopascals. The volume remains constant to be 8 meter cubed. The constant of air is exactly the same, 287 kilopascals meter cubed kilogram Kelvin, and the final temperature remains also constant, so it's 400 Kelvin. Therefore the final mass is equal to 13.94 kilograms. Now that we have the initial and the final mass, we are able to find out what is the mass leaving the system. Mass leaving is simply the difference between mass 1 minus mass 2. And if we take this minus this, we find that the mass leaving the system is 27.87 kilograms. Now that we have the masses, we're going to substitute into the equation to find the electrical energy supplied to the air during the process. Notice that in order to do that, we need to determine the value of the internal energy at the beginning and at the final state. Since the temperature is maintained to be constant, the value for U2 and U1 is going to be exactly the same. Then we go to the tables, A17 for air, and we look at the internal energy for the temperature of 400, and we have it over here, and we find that the internal energy at that temperature is 286.16. Now we need to find the enthalpy leaving the system. That is also at 400 Kelvin. So we go to the same table and we find the value of the enthalpy to be 400.98. All of these are in kilojoules per kilogram. Now that we have all the values, we're going to substitute into this equation. Therefore, the electrical energy going in is going to be equal to the final mass, 13.94 kilograms, and we multiply by the final internal energy, 286.16 kilojoules per kilogram, minus the initial mass, which is 41.81 kilograms, and we multiply that by the initial internal energy, 286.16 kilojoules kilograms, and then we add the mass flow rate, the mass leaving, which is 27.87 kilograms, and we multiply by the enthalpy leaving, which is 400.98 kilojoules kilogram. Notice that the amount of energy entering through the electrical circuit is going to be equal to 3200 kilojoules. Notice that in all the equations, kilograms and kilograms cancel, and that's how we ended up with kilojoules, which is a unit of energy.